So let me just sum up what we discussed last class. So we discussed on the encryption ideas. We give you two small approaches for encryption: cipher, block cipher, and streaming cipher. One of the example was you try to encrypt the statement go, and you can do 1 by 1 character. Shipped by 5 Caesar cipher was discussed, and then those things can be easily broken. Means that someone can easily guess what those encryption algorithm might be. So it might be safer to use a block cipher mechanism, such as I encrypt both characters at the same time as a block. So every single time you might run into different cases, hopefully. So that was idea they give you as they use a key M, M. But M has an inverse matrix, which means it can reverse the original matrix. So using M, you can encrypt that block Go by converting into certain location within the alphabetic order, and blah blah blah. You do a multiplication between matrix, you modulo 26 that gets you YB. In order to bring it back from YB to Go, you use an inverse matrix. We show you a small examples on that part, right? The idea behind this was what? Having only one key. So this use a one key only to encrypt. You use a same key to decrypt the key. So symmetric encryption algorithm discussed. The symmetric encryption algorithm discussed. And then we start discussing. We briefly looked at what RSA key scheme was. So they give you a small pseudocode for generating a key, but difference from the previous matrix block cipher approach was this generate a public key and private key, P and D. So they randomly select some prime number P and Q. They show you the way how to calculate the values that needed for generating public key E, N, and E. You use private key D in order to recover the original messages. And we in your textbook show you a simple way to do this as examples for that. So this approach is asymmetric encryption algorithm. Asymmetric. You need a key, two keys. One key for encryption, another key, separate key for decryption. So those are the ideas, and each representing with examples given. Again, it's going to be difficult to compute this without any calculators. So there will be a low chance that I might ask you in the final exams, but you should know. You should know. Okay, that was pretty much it for this chapter. We discussed start from internet, some interesting things going on the internet, DDoS, worms, viruses, basic ideas. I try to give you a bit more details than the textbook. Textbook didn't cover too much on the internet security parts, but I add some extra slide to give you more ideas. And then asymmetric, I just describe it. Okay, I think that's good enough for last chapter. So just a review of last week. And hopefully, 가만있어 봐. When is the assignment 4 due? Assignment 네 번째가 언제까지였지? 6월이에 다음 주구나. 다음 주. Okay. I think you will be able to finish your assignment 4 at this point. And we give you assignment 5 this week as well. Okay. Let me go to the next chapter. So, next chapter, we're gonna discussing something called computation models. Well, we've been discussing an abstraction from the beginning, so you guys are a bit familiar with the idea of having a model or making things a bit easier to understand. Here, we're going to explain the purpose of constructing a model, and they're going to bring up something new, something called a Turing machine agent. They're going to keep calling it as machine and agent, computing agent for those models. So in the first few chapters, we've been discussing for constructing an algorithm, pseudocode, and you get a pseudocode, and then you write your own algorithm, and then you could translate that into programming languages, right? High-level languages. So you are actually already done that, but when you actually try to write down the algorithm, you're gonna replace that into instead you're gonna build something called Turing machine. So writing down algorithm now is going to replace as writing down the machine, Turing machine. So later we'll discuss some thesis that if you can describe certain solution to a problem using Turing machine, then there is an algorithm to it as well. So it will be much more clear when we start seeing the examples. So list the required features of the computing agent, simple machines. Describe the components of the Turing machine and explain how a good model of a computing agent. How do you build a computing agent? Another way of saying how do you build your own algorithm, and in different ways. List the features of the algorithm. Explain how Turing machines more dynamic한데, 꽈강 dynamic한데. List the features of the algorithm and explain how the Turing machine program matches them. Even though we haven't discussed that much, it seems the algorithm and Turing machine seems to be same thing. 나중에 나오겠지만 그 problem, it's given problem, 솔루션을 하는 거를 무슨 알고리즘을 짜라고 하잖아요. 그 문제를 풀기 위해서. 근데 튜링 머신으로 그 문제를 풀 수가 있으면 그거에 맞는 알고리즘도 분명히 있어요. 그럼 나중에 이론이 나와요. 이 뒤에. Simulate the operation of a simple Turing machine on specific inputs. I'm going to give you some examples of the Turing machine itself. Construct a simple Turing machine from specification, both writing the rules and drawing state diagrams. Computer programs, algorithms can be represented as this. State diagrams. It simply consists of two things, node and some edges. This is state 1, this is state 2. If I do something here, I will go to this state. If I do something else, I don't know what, 3 states. I can describe the current status of the algorithm solving using this. This is a very similar design to a state diagrams. 내가 뭘 하냐에 따라서 내가 여기 있다가 뭘 하면 그 옆으로 가고. So how can we use that thing to describe a Turing machine? So what is a Church-Turing thesis? State the Church-Turing thesis that explain what it means. It's a bit difficult. They involve some of the proving certain thesis, certain theorem. 증명하는 것도 약간 나오고 해서 약간 복잡해요. Justify why computer science believe Church-Turing thesis is true. Explain what unsolvable problems. There are certain problems doesn't have a solution to it. Can't do it. How can you prove that your problem doesn't have a solution? 증명하면 어떻게 돼? 어떤 문제에 답이 없다는 걸 증명하라. 그럼 어떻게 해? 애매하죠. They're gonna use a Church-Turing thesis to show that something is not possible or possible. Describe the halting problem. What inputs and outputs? Halting, finishing a problem. So halting is also a very difficult problem too. Can you prove that your program will end? Someone give you the algorithm or program and ask you to make sure that your program ends in good state. Means that they will display the outputs in the way that I want it and finish itself. Can you prove that your program will end? 자기 프로그램이 끝나는지 안 끝나는지 증명해 보라고. 증명을 할 수가 있나? 되게 이상한 얘기 같죠. 1 더하기 1 증명하라는 얘기랑 똑같은 얘기 같죠. There is something called halting problem. Halting also means to finish. 요즘에는 컴퓨터 끌 때 어떻게 꺼? 윈도우 메뉴에 뭐라고 써 있어? 컴퓨터 끄기 이렇게 돼 있죠. 영어로 보면 뭐라고 돼 있어? 파워 오프는 완전히 그냥 뽑는 거고, 파워 오프는 막 이렇게 그냥 눌러서 끄는 거고, 소프트웨어에서 끄려면 아마 보면 shutdown 이렇게 써 있잖아요. 영어로 보면. English Windows they probably say shutdown. Any other computers, Linux, Windows, you can also put shutdown command as a shutting down the system, or you can type in like halt. 시스템에 어떤 컴퓨터 리눅스 끄고 싶을 때 셧다운도 쓸 수 있지만 halt라고 치면 컴퓨터가 꺼져요. 다른 단어라고 보면 돼요. 셧다운의 다른 단어. 끝나는. So how can I prove a halting problem? What is a halting problem? Explain why a halting problem cannot be solved by any Turing machine. Why can you not prove that halting problem is not provable by using the Church-Turing? This is complex. We'll discuss a little bit later. So first, we're going to show you how to draw all this. Why we need this. So introduction, there are problems that have no algorithmic solutions. No algorithmic solutions. But there 얘기하지 않았나? What might be the real life examples that doesn't have any solution? No algorithmic solution. 몇 번 얘기하지 않았나? 안 했나? 택배 아저씨 problem, scheduling problems. 그거 내가 얘기 안 했어? 안 했어? 했죠? 그죠? Those, if you are asked to build a computer program to schedule the best path for those deliverables, there is no single good perfect algorithm to solve that situation. 그죠? Of course, there are programs that actually give you some suggestions, but there is no guarantee that's the best solution possible. That is probably the closest as possible approximation. So we can prove that no algorithm could ever exist to solve certain problems. So we can prove that certain problems cannot have a algorithmic solutions. 그걸 왜 꼭 prove 해야 되는지 모르겠는데 prove 한대요. To study what computing agent and cannot do, and we must strip them down to bare essentials. Try to understand the basic model of computation. Create an ideal computing agent, model of a computing agent. This is how your actual computer is built in theory. What is a model? Model of something. Capture the important property of real things. Models. Abstraction. What was an abstraction? Even asked for your midterm exams. 그죠? Abstraction. A lot of people didn't get it right though. 야, 별의별 답을 다 써놨더라. Right? Abstractions. So if you think about it again, you try to make things a bit easier. This is like a model too. I usually bring up the Facebook or Twitter. If you follow your friend, Twitter에서 follow 그러지? Or if you make a friend with someone else's, then you have a relation to that person. 그렇죠? So if you log into Facebook webpage, the first webpage they usually say 이렇게 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 하지. So you are connected to these people, right? In terms of abstraction, I can do this too, right? 그죠? Abstraction. Well, we're just gonna say this is one entity, you're human beings. If there's a line between, I'm gonna say there is a relationship. I'm gonna forget about any other details that describing this, like follow 하거나 뭐 friends인데 뭐 bandit friend나 뭐 I don't care about those conditions. As long as we have a line between the two, there is a relationship. I just did an abstraction of the problem. Modeling of this abstraction models. How can I describe this figure? It says model is capture an important property of the real things. I capture this triangular property of the three people. or things that I can describe in this graph is this node A has two friends. Means that it has two edges in and out of from them. So I just describe the property of this graph itself. So as soon as you draw that, you did the abstraction, you just start describing the model itself. Nothing fancy. 어려운 게 아니에요. 벌써 모델 만든 거예요. 세 명이 커뮤니케이션 할 수 있는 모델. 나왔죠? 실제로 여기 사람이 들어가야 되지만 사람 대신에 점을 이용해서. Differs in scale from the real things. Well, I kind of ignore all the minor details of the originals right here. Whether they're actually friends or not, I don't care. As long as they have a line, I'm gonna assume that they are friends. Omits some details of the real things, same. Lacks some of the functionalities of the real thing. So make it easier so we can apply a certain type of algorithm on top of it. So if I build using your friend's Facebook map, I create this abstracted model. I create this graph. Maybe this is you. What is the power of having a model like that, building a structure like that? Assume this is you. This is your another friend's B. Well, people that you don't know. People you don't know, you never know of. But it might be a friends of your friend's friends or something. So what if I wanted to send a certain message to this guy? What is the fastest way that I can do? Fastest way that I can send a message to this guy. I don't know this guy, but I think I can still send them a message through the multiple friends. 그렇죠? Okay. If you're given that problem, I ask you to build an algorithm to find a path between the two. Why is it so strong? Why is it so powerful? Well, if I looked at it, because I described the problem in this way, maybe I can use a Dijkstra's algorithm on top of it. 그지? 내가 이 문제를 이렇게 단순화 시켜 놓으니까 기존에 있던 shortest path algorithm 그냥 갖다다 쓰면 되죠. Maybe I can run that shortest path searching algorithm path right there. So depends on how the level of abstraction this way, then you can use other techniques already out there to solve your problem in here. That's a simplified version of a model and abstractions. Models can be also used for predict a behavior. Look at the model's behavior. Maybe safer, less expensive, less difficult than real thing. What is model prediction? 뭐 이런 거 많이 나오는 분야가 뭐야? Model prediction 이런 거 많이 나오는 분야가. You see it every single day from news or website. 날씨, weather forecast. They usually say they have a certain model so they can predict tomorrow's weather. But what are those models are representing? 그런 모델이 뭘까? 거기서 얘기하는 모델이. 옛날에 뭐 아주 간단한 모델 이런 거 있을 수 있겠지? 내일이 며칠이지? 29일? 2013년 요즘 몇 월이야? 6월 29일. 6월 29일 날씨가 어떤지, 2012년 6월 29일 날씨가 어떤지 쭉 가지고 있죠. 모델이지 뭐. 그 중에서 오늘 날씨랑 가장 비슷한 내일 날씨 확인해서 아마 그럴 것이다 하면 prediction, right? I just described the property of the previous year's the same day weather and use the property to predict the next day's weather on the same date. Simplified version of the models. Of course, the actual real weather forecast is really, really complex. They had to consider many different factors. That's why they need a supercomputer clusters to do it. So, 왜 그런 얘기 많이 하잖아. 예측할 수 있는 모델을 만드는 기술이 부족해서 맨날 틀린다고. 기계는 좋은데. 맨날 그런 얘기 하죠. Same thing. Models let us test something without building it. So we can simulate. Because we know all the properties, we can change some of the properties within the model and see what's going to happen next. But if you just try to focus on the prediction too much using the model, sometimes it's not right. 너무 예측하는 거에 포커스를 잡고 모델을 만들면 당연히 안 맞겠지. 모델이 어떻게 뭐 여러 가지 생각지도 못한 팩터가 많기 때문에 하죠. 근데 그 현상 자체를 표현하는 데 좀 집중해서 모델을 만들면 그게 훨씬 더 효율적일 수도 있어요. So even though your textbook says models can be used, your textbook says models can be used as a prediction, but it's not the only purpose. It's just way to describe the current as it is situations. So model of a computing agent. Your program, like how can you describe your program? It has a key features of the computing agent. Read input data. You enter some values in. Your program will read input data. Store and retrieve the information in the memory. 그죠? I read the data, I put that in the memory. See? And then before I put that in the memory, I translate all the instructions. Compiler, binary instructions, right? And then perform based on those, whatever written on the memory, you program and run, output the result. This is a simple model of your program. Every program follow this. 그지? 컴퓨터에서 돌아가는 모든 프로그램이 이 모델을 따르고 있지. 그죠? 인풋 주고, 인풋을 읽어서 프로그램을 돌릴 때 instruction set으로 다 매칭해가지고 0101 만들어서, 바이너리 만들어서, 메모리 올려주고, 메모리 올려준 거 돌리고, 결과값 나오고. Pretty much every program following this model. So it's a model of computing agent. 컴퓨터 돌아가기 위한 모델. 물론 프로그램들이 세부적으로 들여다보면 다 틀리겠지. MS 오피스랑 여러분이 참 프로그램이랑은 차이가 많겠지. 그치? 그래도 기본적인 모델은 똑같잖아. 그죠? 인풋 받아서 메모리 올리고 돌리고. So hopefully that gives you idea of modeling, simplified version of this procedures. So they're gonna bring up something called one of the models they're gonna want to describe is Turing machine. It's a model of a computing agent. It's a model of a computing agent. We like to compute something. We like to find out certain values in it. So it has a tape infinite in both directions. So it's going to be look like this. It's a tape. And it can go both directions. Maybe there is an indicator right here. Each cells of the tape holds one symbol. I don't know. It may have A, B, C, D. Tape alphabet, finite set of symbols for the tape. So symbols are finite. Symbols probably, in this case, A, B, C, D. It's a tape computing agent. Tape holds an input and memory. So we can put this on top of the memory. Examples will come in next slide. It will be easier. Has a finite number of internal states. So it can be describing using this finite number of states. Like that. So if I'm pointing to an A, I tell this machine to move one right. Okay. Then the current value that I'm pointing at will be C, right? So the first stage I was pointing to an A. Next stage moving to a right. Give me this another state, but state value will be C. I can go right again if I want. And this is the state 3, state 2. Each state is representing in different status of this tape. 여기서 만약에 왼쪽으로 가고 싶으면 어떻게 해? maybe I can create another state. 6 left. If I go left, 아니다. left 하면 막 이렇게 한번 해보자. left. 근데 when I'm here, I go left, I go back to A. 그지? 여기서 또 이렇게 가면. Then instead of making another state going left, what if I just simply say left? I'm going back to the original state. So it says, in order to perform this activity, we can use a finite number of states. 1, 2, 3. I don't know how many states will be necessary, but 6 doesn't sound be necessary. Just give you a very simple way of just reading the definition. This might be working in this way. 알제브라 프로그램도 똑같아. 첫 번째 라인 읽고 두 번째 라인 넘어갈 때 일로 오는 걸로 표기하고. 그렇죠? int A, int B, 1. 그럼 int A 첫 번째, 두 번째, 첫 번째 라인 두 번째 가고 세 번째 뭐 for loop 있으면 for. 세 번째 스테이트가 아마 for loop을 얘기하겠죠. 일로 다시 돌아가나? 다시 저기는 못 돌아가겠지? Same thing. We never tried that way. We just simply used from high-level languages before. Has a finite number of internal states. Instructions for the machine. Examine the current tape symbols and current status. Current state. Examine the current tape symbols. 지금 현재 가리키고 있는 symbol, probably A. I'm starting from A. Write a new tape symbol and changing states and moving left or right one cell. So they give you this instruction. This machine can perform these activities, these two. Let's take a look. Turing machine examples like this. 이거 뒤에 나왔어야 되는데 왜 이렇게 앞에 나왔냐? I don't know what that means, but in this state, if the current symbol is B, if I read input value is 1, and if I go right, then I go to state C. Whatever that means, whatever this is doing, this is a Turing machine examples. So this actually will solve a certain problem. We're gonna take a look at 3 different examples of a problem. First thing is probably they want you to build a Turing machine, or another way of saying that they want you to build a small program that converting every bit. So input value is like this. Input value is 5 zeros. They want you to build a program to convert everything to 이걸로 이제 할 수 있을 거예요. 다음 예제가. Before they ask you the pseudocode, this time they ask you to draw this Turing machine in order to compute that. So this is actual Turing machine look like. Current state is 1. The symbol is 0. If I move 1 right or left, I can go back and forth. So I'll be staying within the page. While I'm moving into another position, I can print out certain outputs. 뭐 0이든지 1이든지 찍어낼 수가 있는 거예요. 한쪽 옆으로 가면서 찍어낼 수 있는 거예요. 결과값을. So this is Turing machine instruction ways. If in state I and reading symbol J, then write symbol K onto the tape, change to state S, move in direction D. state I에 있고, 지금 뭐 예를 들어 state 1에 있고, 지금 읽은 값이 J면 K라는 거를 테이프에다 쓰고 state는 그 옆 state로 가고 그게 오른쪽이든지 왼쪽이든지 움직이고. In order to describe this, they're gonna call it as, they're gonna write it down IJKSD. Direction, next states, the symbol they're writing, the current symbol and current state and the symbol they're reading into. 예제 보면 훨씬 깔끔해. Next page. So it's like this. So this is one example. If the state is 1, this is the current instruction. This tells this Turing machine to do what? If it's in state 1 and reading value is 0, see? State 1 and input value is 0, write 1 to the tape. 여기다 가리키고 있어요. Write 1 to the tape, change the state 2 and move right. 옮기면서 1 쓰고 여기서는 오른쪽으로 가고. State는 now 2. Instructions. This tells you what to do for this machine. This tells the machine to move right, left, and which state they're going to be in. So later, when I ask you to do a program in Turing machine, you will give a set of instructions like that. 저걸 이렇게 쭉 적어놓는 거예요. This will representing the state as well. 예제 보면 훨씬 쉬워. 예제가 먼저 안 나와서 좀 헷갈릴 수 있겠지만 예제를 먼저 볼까? 거꾸로 하는데 그러면? Let me do the one example first and then go back to the slide. Okay. So Turing machine examples to show what Turing machines can do. First program, I'm just going to take a look at the first program. It's something called bit inverter. Flip bits, 0 to 1, 1 to 0. They want you to write a program can do that in Turing machine. And state diagram is a visual representation of the Turing machine algorithm. This representing what's happening in this tape. 이거는 여기서 무슨 일이 일어나는지 따라가면서 볼 수 있게 만드는 state diagram. Bit inverter, the condition they give you, this is algorithm description, I guess, pseudocode description. Given a string of zeros and ones, change every 0 to 1, every 1 to 0. Flip it. Okay. Algorithm ideas. Move right, flip each bit as it goes, and stop when you reach the blank. So from the start left, reading 1 bit at a time until you hit the end, you're going to flip every single bit. Okay. So that's the pseudocode, right? A brief pseudocode. Include the no rules that responds to the blank symbols. The machine must stop when input ends. So you don't need to specify conditions whether it hits a blank. 아무것도 없는 걸 갔을 때 뭐 하라고 얘기 안 해줘도 the machine itself will terminate. Okay. So they simply say don't worry about it. You don't have to write down the state for there is no input. So if you draw that, this is going to be like that. My state is 1. The current state is 1. 갑자기 뛰어넘었지. 나도 헷갈리잖아. 1, 1, 0, 1, R. 1, 0, 1, 1, R. Let's say input is 0, 1, 0. 아니야. 0, 0, 1. Okay. I'm gonna draw a state diagram. It seems there is only one state. I don't know why. Let's see. From state 1, if the reading value, the current value is 1, change to 0. My next state is still 1, and moving 1 right. So if the current value is 1, I'm going to change it to 0, but I'm going to move 1 right. But my state will stay the same, 1 state only. That's why I put like that. Likewise, for the 0, if the current state is 1, the reading input value is 0, I'm going to change to 1. State still 1. So 1 아니다. Yeah, 0, 1. I'm keep going this way. So R. So whatever I do, I'll be staying in this state. 그럼 이거 그대로 읽어보면 해보자. The starting state is always 1. There's only one state. Okay, 0. I'm reading this. 0 to 1. Okay, I'm gonna change to 1 and move this to right. But I'll be still here. Again, next value 0 again. So I take this path 0. Same thing. I change to 1. Moving 1 right. Again, my next state will still be 1. Okay. So while I'm staying here, my next value reading is 1. So I should go this way. 1. I should change to 0. I have to move to right. Next state is still 1. But it says in the previous slide that if you hit a blank, nothing. It says Turing machine will recognize that as a blank machine and it will terminate itself. So I don't need to write it down here. If I need to consider this as an option, then I might need to do something like this. 만약에 이게 블랭크 하는 게 없었다면 이렇게 해야 되겠지. 0, 1, 0, 1, 0, 0, 0. 0이 나왔을 때, 0이 나왔을 때, 1이 나왔을 때는 어디로 가라고 다 표시가 되어 있는데 블랭크 나왔을 때는 없잖아. 그럼 뭐 만약에 위에서 전제를 안 해줬으면 이렇게 돼야 되겠지. 새로운 스테이트를 만들어가지고 블랭크일 때, 비어있을 때 아무것도 하지 말고 좀 애매해지지? 또 오른쪽으로 가라. 끝내야 되는데 아니 뭐 이렇게 해놔도 되지. 계속 이렇게 하든지. 근데 이거 의미가 없잖아. 계속 빙빙 돌 거 아니야. 이러면 program doesn't end. 끝나는 게 없지. That's why the previous slide says even when you hit the blank, it will terminate itself. The Turing machine knows what it does. Halt the problem. It just describes your program in the state diagram. Depends on the program, you might need a multiple state. Depends on the program, it might need a multiple state. 그러니까 아주 간단하게 생각하면 나올 수 있는 모든 경우의 수를 다 이걸로 표현하는 거야. 0이 나왔을 때는 일로 가세요. 1이 나왔을 때는 일로 가세요. 단 이 경우는 너무 좋아서 하나만 있어도 돼. 하나만 있어도 다 해결돼. 혹시 모르니까 3이 나올 때는 오른쪽으로 가세요. 뭐 4이 나왔을 때는 오른쪽으로 가세요. 이렇게 둘 수도 있겠죠. 만약에 0, 1 대신에 다른 걸 넣을 수 있다면. 근데 아까 전에 초반에 나올 때 인풋은 0, 1, 0, 1밖에 안 된다고 했으니까 이거를 쓸 필요가 없죠. 똑같이 알고리즘이지. 똑같죠. 알고리즘을 이제 이렇게 표현하는 거예요. State diagram. State diagram. 됐지. 옛날에 프로그램 이렇게 했겠지. 그렇죠? 옛날에 테이블로 이렇게 했겠죠. 이건 아주 간단한 프로블럼 솔빙이니까. 그래서 예를 들면 01, 01 찍혀 01, 01, 01 적혀 있는 테이프를 쭉 가져다가 이렇게 손으로 직접 하나씩 툭툭툭 오른쪽으로 하다 보면 01, 01이 반대로 나왔겠지. 그죠? 계산기 초반에 만들기도 비슷했겠죠. 근데 이게 답이 이렇게 나와 있으니까 이렇게 하지. 만약에 please draw your own Turing machine 하면 state diagram 하면 사람들이 이렇게 많이 해요. Same problem, draw your own state diagram to describe your Turing machines 하면 사람들이 대부분 이렇게 많이 시작해요. 0하고 1이니까 두 개는 필요하겠지? 이렇게 시작해요. 1일 때 1 보면 0으로 바꾸고 오른쪽으로 가는데 스테이트는 두 번째로 가고 2번 스테이트로 가고. 오케이. 그럼 여기서 어떻게 해? 여기서도 1이 나올 수가 있고 0이 나올 수가 있죠. 그럼 여기서는 어떻게 해야 되나 보고 그냥 여기만 다시 돌아가지 뭐. 1 R state 1. 그럼 여기서 0이 나오면 어떻게 해? 계속 빙빙 도는 거지. 0이 나오면 어떻게 해야 되지? 0이 나오면 그냥 또 스테이트 하나 또 만들어 줄까? 그냥 이러고. 세 번째 스테이트는 0일 때. 그렇다고 막 다 꼬여요. 이렇게요. 스테이트 4개 나와요. 근데 하나 좋은 방법은 하나의 스테이트로 표현할 수도 있는 방법이 있죠. 매번 움직일 때마다 다른 초이스가 나오니까 거기에 맞는 이 스테이트에서 갈 수 있는 모든 경우에서는 다 정해줘야 되는 거죠. 이렇게 좋은 게 있는데 왜 저렇게 고민해? 근데 so it doesn't mean your algorithm is bad. You can still build a Turing machine that using a multiple state. I think it's possible. You can take a look at this as your programming assignment too. Someone's programming is short. Someone else's programming is long. But they actually doing the same thing. 숙제들 다 걷어서 보면 프로그램이 다 틀리지. 어떤 사람들 프로그램은 길고 똑같은 거 하라고 그랬는데 어떤 사람은 길고 어떤 사람은 짧고 길고. So there is no one solution only. You can build a multiple solution using different number of states. Doesn't really matter. But they show you it could be the way of comparing the efficiency. 어느 게 더 효율적으로 잘 쓸 수 있는. 디버깅 할 때 좋겠지. 자기 알고리즘이 어디서 잘못되는 경우가 있는지 없는지 이렇게 표현을 하면 확실하게 잡아낼 수가 있을 거 아니에요. 스테이트 다이어그램은 이래서 상당히 강력한 툴이에요. 강력한 모델을 하는 방법이에요. 근데 디버깅하면 어떻게 머릿속으로 디버깅하지 프로그래머가 여기서 이거 이렇게 하면 다음 줄로 갔다가 폴업으로 들어가면 다시 위로 올라오고 막 머릿속으로 이렇게 하지. 디버깅하면. 그거를 쉽게 손으로 쓸 수 있게 할 수 있는 방법 중에 하나예요. 그죠? 상당히 강력한 툴이에요. 모든 경우에서를 생각하게 만드는. 그러면 실수가 좀 줄겠죠? So this is one of the example for Turing machine for fit inverter problem. So this is my state diagram of describing this. And this is my Turing machine instructions. 2 lines. I just did my first program. This is my computing agent. computing model. 나온 거 보면 bit inverter problem. Each row shows the contents of the tape after a move. Head position is shown in the ball. The always state 1. 지금 이거 보여준 거 그대로예요. It doesn't matter where you go. Your state always be 1 because there is only one state. So they try to show that in here. This is a second example. Let me go back to the slide where we jump off. Now it makes sense, 그지? This is the slide that we skipped. Now it makes sense. It just teaches you the way of telling what Turing machine should be doing. The Turing machine instruction sets. 이게 프로그램이지 뭐. This just describe the how many state that you need as well. 그치? 이것도 마찬가지로 moving right, left. So it also makes sense now. It reads an input from a tape. It uses a tape as a memory, then read and write. So I changed the symbol 0 to 1, 1 to 0. It's like a memory. So tape is now a memory. memory 여기다 0101 바꿔가면서 0일 때는 1로 바꾸고 1일 때는 0으로 바꾸고. So it's the same thing as a memory. So tape is my memory. Read and write. It takes an action based on its states and its input. Depends on what input that I have. I can decide whether I should go right or left. So that's up to me. That's up to my programming. Here. It can produce an output on its tape. So at the end, when we're hitting the blank lines, there is nowhere to go. Finish, halt. Then whatever left on the tape will be my output. 그지? 0, 1 다 바뀌었으니까 this will be my output. Done. It satisfies all 4 conditions for a computing agent. Read input, write something to a memory, execute, and produce an output. 아까 본 4개 스텝이랑 딱 맞죠? It just satisfied all the conditions for computing agent. 그래, 순서를 다음에 바꿔야 되겠다. 근데 예제가 먼저 나오면 갑자기 헷갈릴걸? 이건 또 뭔가 싶고요. So a model of a algorithm must be well-ordered collections, consist of unambiguous and effective computable operations. All the operations on in this tape is clear. Either left or right, change something to the something else. Quite clear. 이거 뭐 헷갈릴 게 뭐가 있어? What can you do to make ambiguous instructions on this state diagram? 이렇게 그려놨어. 아 좋아, 딱 좋아, 딱 좋은데. Can I make this as ambiguous instruction? ambiguous하게 만들려면 어떻게 하면 되겠어? What does it mean to have ambiguous and unambiguous in this state diagram? 이렇게 하면 어떨까? 하나 더 해. 그럼 어떻게 해야 돼? When I see one, should I go this or should I go this? I just make a very unambiguous instruction to the Turing machine. It's a machine dumb. It only goes what you tell you to do. But I tell them very confusing solutions. You have to choose one. 그치? 이렇게 해놓으면 어떻게 돼? 같은 인풋에 대해서 갈 수 있는 방향의 초이스가 2개를 만들어줘 버렸잖아. 그럼 ambiguous지. 그러면 this is good algorithm or not? It's not an algorithm anymore. So when you're analyzing this type of state diagrams or the instruction sets, this is one way to take a look at it. 뭐 예를 들어 input 하나에 딴 데로 가는지. Turing machine, this is not allowed. But 나중에 나오는 state diagram 중에서는 2개가 가는 경우도 있긴 있어요. 2가지 초이스를 줄 수 있는 경우 있어요. 멀티플 초이스 줄 수 있는 경우 있어요. 그거는 나중에 아마 평생 안 할 거야. 웬만하면. 그냥 맛배기만 보면 어떤 게 있을 수 있겠어? 예를 들어 1, 0, R 들어왔을 때 또 하나 또 있어 이렇게 스테이트, 세컨 스테이트. 지금은 튜어링 머신은 둘 중에 하나지만 당연히 알고리즘 unambiguous 해야 되니까 확률로 할 수도 있겠지? 한 30% 확률은 들어오는 횟수에 따라 30% 일로 가고 70% 일로 가고 여기로 가면 이제 신세계가 펼쳐지고 이렇게. 실제로 나중에 통계를 이용한 저런 머신들도 존재합니다. 통계를 이용한 머신도 존재해요. 근데 우리는 아니야 지금. So its model must be well-ordered collections, consist of the unambiguous and effective computable operation, clear instructions, and then it should finish in finite amount of time. Well, it does say when it hits a blank, it will terminate itself. It says so. 아니면 계속 빙빙 돌면 it's not end of program. 아까 전처럼 여기 하나 달아갖고 블랭크 할 때마다 계속 돌아가게 만들면 어떻게 돼요? 인피니트 룹이랑 다를 거 없죠. 계속 그 안에 있는 거니까 스테이트 계속 그 안에. Produce a result. I have my result right here in my tape. Done. 네, 설명한 거 그대로 있네. 네, 바보다. 내가 잊어버렸다. Be a well-ordered collection. Starting state and position on the tape are well-defined. Where to start in the tape? Are you starting from the rightmost location or leftmost location? The starting state and position on the tape are well-defined. Where to start, where to end. At most, one rule can match a given state at a position. At most, one rules only. One rules only. It is well defined what happens if no rule matches. If there is a 2 certainly comes in, it should tell me what to do. It should tell me what to do. 근데 여기서는 2 나올 수 없죠. 2 is not possible because we define from the beginning the symbols that allowed in this tape is only 1 and 0. Turing machine knows where to start and what step to do next. I should go to state 2, 1. Turing machine just simply following these arrows. Consists of the unambiguous, effective computable operations. Turing machine instructions completely specify what machines should do. Don't make a complex computing instructions. 뭐 이렇게 써놓는 거야. 아니면 뭐 left로 가든지 뭐 이렇게 써놓는 거야. 완전 말도 안 되는 거죠. Clear. Turing machine instructions cannot be ambiguous. Has to be unambiguous. Halted finite amount of time. Program must finish in given amount of time. If doesn't finish in finite amount of time, that's your infinite loop problem. Program doesn't end. That's a problem. Turing machine goes on to the infinite loops like a poor attempts and the algorithm. 근데 프로그램 잘못 짜면 for loop 컨디션 잘못 써져가지고 계속 빙빙 돌죠. 그죠? We can ensure halting for inputs within the scope of the problems. 이것도 찜찜하면 이렇게 해주든지. When you see a 1-1 at the end, it means I finished my program. 뭐 이렇게 extra condition, you can add an extra condition, or if you're unsure, if you see this character, end of line. Why do you think C has this? C 왜 저거 했겠어? 끝나는 표현을 알려주고 싶으면 모르니까. 그래서 필요 없는 건데 꼭 그때 들어가 있는 거지. 돼 있는 거. Tells you where to end. Also tells you where to stop processing for your expressions. So everything is there for the reasons. 컴파일러 나중에 저렇게 짜면 진짜 머리 빠질 것 같아요. 그래서 나는 컴파일러는 안 했어요. 아까 막 이렇게 막 짜고 하잖아요. 그런 프로그램도 있어. 스테이트 다이어그램 이렇게 해주면 간단하게 프로그램을 짜주는 애들도 있긴 있어. 그러니까 동그라미랑 이걸 그리면 돼. 컴퓨터에 프로그램을 짜는 대신에. 이렇게 하면 간단하게 쭉 나오게 할 수. 대신 안에는 채워 넣어야 돼. 안에 어떻게 하는 건 채워 넣어야 돼. 그래서 요즘에 큰 프로그램 짜는 사람들 저런 거 많이 이용하죠. 코드를 직접 쓰는 게 아니라 틀을 잡아주는 거예요, 저렇게. 틀을 잡아주면 껍데기 코드가 이렇게 생겨요. 껍데기 코드가. 안에 비어있어. 펑션 뭐 이렇게 다닐 거. 껍데기만 생겨. 그럼 이제 아래 사람들한테 너 이거 안에 채워 넣어라 이렇게 해갖고 사람 나눠주면. 원래 그게 맞는 방법 중에 하나예요. Produce a result. Contents of the tape when Turing machine halt and output. Done. Thus, Turing machine program is a good model of an algorithm. It's a model of an algorithm. It's just doing everything what algorithm is doing in simpler format. 그치? It's a bit simpler format, easier to follow. So Turing machine is a good model for algorithm. Good model for algorithm. Very, very powerful model for describing the algorithm. 아까도 계속 얘기하지만 굉장히 강력한 모델이에요. 이런 거 신경 안 써도 되잖아. 내가 뭐 제대로 타입을 했는지, int a 다음에 이걸 빼먹었는지 이런 거는 다 제끼고 알고리즘이 돌아가는지 안 돌아가는지를 확인할 수 있는 거예요. 굉장히 강력하죠. So we already take a look at the bit inverter problems. Let's go to a parity bit problems. Second set of problems. 어디 갔니? Parity bit problems. Let me guess. Okay. So parity bit says given a string of zeros and ones, still a 0, 1, 0, 1 input, count whether number of ones is even or odd. So how many ones are there? If it's even, add 1 to the end of the string. If it's odd, add 0 to the end of the string. 그죠? Clear instructions. 1이 4개면 끝에 1 하나 더 써갖고 1 5개 만들어주고. 뭐야? 또 뭐야? 아니면 그치? 아니면 0을 끝에 넣어주고. 그쵸? Algorithmic idea, state 1, before I add this, even though you already have the next step. In order to program this, how many state do you think you will need? 스테이트가 몇 개나 필요할까? Guess. I can only guess too. 스테이트가 몇 개가 필요할까? Okay, let me see. I don't know what's going to be exactly. Maybe I need a one state counting number of ones. Okay, I don't know how, but I think it's reasonable. Okay, if I need a one state counting number of ones, maybe I need another state of counting number of zeros. 그죠? That's what it's required. Maybe another extra state to write down 0 or 1. Maybe 3, if it's possible, or 4. I don't know. I have to try. Solution they give you in your textbook is done this with the 3 states. Done this with the 3 states. Again, because they give you the solution, the looks easy, but without any state information, it's going to be very complex. 별거 아닌 문제인 것 같은데도 그냥 문제만 던져주고 스테이트 다이어그램 그리라고 그러면 스테이트 10개씩 그리는 사람도 나와요. 왜냐면 하다 보면 자꾸 여기서 다른 경우가 또 나오네, 경우에서 또 나오네 하다 보면 스테이트의 암흑 속으로 가다 보면 스테이트가 이제 뭐 날아가는 거지. 근데 you must have a finite number of states. 그치? That was a requirement for Turing machine. Only finite number of states. You cannot have infinite number of states. 스테이트를 무한대로 가지고 있으면 뭐하러 이거 해. 계속 나오는 스테이트만 새로운 거 그려가지고 가져가지. 그렇죠? 근데 you have to terminate your problem within given number of, the finite number of states. 그러니까 문제 풀기가 어렵지. So algorithmic idea, state 1 representing even parity or so far. So they did a slightly different way. Well, I guess I was partially right, but so they think that one state for counting even or odd. Even or odd. So 2 state. Reading 0 doesn't change the state. Reading 1 change from state 1 to 2 and vice versa. 어렵다. 글로만 써놨는데 벌써 어렵네. That's why this wonderful model is easier to think. 이건 더 어렵네. Okay. Start from state 1. If I see a 0, 여기 따라가 볼까 한번? 귀찮은데. 뭐 아무거나 한번 해볼까? 또 00 해볼까? If I see 0, I'm not gonna change anything. 0 is 0. Go to right. 아이고 어디 있어? State 1. See? Okay, I'm still in here. Next character is still 0. Move right. 0, 0, right. So state 1. Next one is 1. I see a 1. I'm not gonna change anything. I'm not changing any inputs yet. 1, right. Go to state 2. When I see a blank, next one is blank, B. Change to 0, moving to the right, state 3. Okay. And at state 3, I don't have anywhere else to go. 그죠? 여기서 끝났죠? So done. Halting the program. Just did what the program asked you to do. Even number of zeros. Even number of zeros at 0 at the end. 맞나? 맞았지? Program done. Input, output that I want seems okay. In order to verify that whether this is working or not, maybe you need to try more samples, more inputs to do it. 책에서 써놨으니까 맞겠지. 다 테스트 해봤겠지. 이거 해보다가 안 되는 케이스 나오면 얘기해요. 그럼 책이 잘못된 거니까 얘기해야 되니까. So those 6 instructions describing this diagram, you see? Each case they tell you what to do from each state. So it's basically they describing these direction edges one by one. Okay, so next set. Okay, so we have one more Turing machine examples left. I'm gonna continue on the next class, and then we'll discuss for the church Turing thesis and finish this chapter next Monday. Okay? Any questions today? 질문? Okay. Thank you. 수고하셨습니다. 네.